Howdy, howdy. This is Mr. Potter. In our last video, we talked about two types of sorts. One of the types of sorts we talked about was the bubble sort. The idea that we just use simple nested loops and a test to see if we need to swap, we do swap. It's not a very efficient algorithm, but it gets the job done, and it's probably the easiest one to program. And the other one we talked about was the selection sort. The idea behind the selection sort is we go through our list to find the smallest number and put it where it belongs, go through the remainder of the list to find the second smallest number and put it where it belongs. And it's also a very good technique. The problem with both of these loops is that if the list is not already, or if the list is already sorted or mostly sorted, these loops are very inefficient in that they kind of just, they have to go through all of the motions. They have to go through the list.length minus one number of times to make sure that everything is sorted. Now, it would be really nice if there was some type of search that didn't have to do that. And luckily, there is a type of search which is called the insertion sort. So I'm going to go ahead and talk about how it goes here. So the idea behind the insertion sort is envision that I've got a list of numbers, like I've got we have a 5, 9, 1, 4, 2, 8, 3, 7, some list of numbers like this. What I'm going to do is I'm going to make sure that the first two numbers are in order. And then I'm going to make sure that the first three numbers are in order. So I'm going to make that, put the 1 in front. Basically, everything else has to get shifted downwards to accommodate that. And now I want to put the 4 in order, so that means the 9 has to get shifted downwards, the 5 has to get shifted downwards, the 1's not going to get shifted downwards. But essentially what happens is after each step, the first 4 elements, or the first 5 elements, so the first 6 elements are going to be in the proper order. So I need to insert a 2, I'll insert it here. Then I've got an 8, an 8 would be inserted here. And then I've got a 3, I need to insert a 3 here. And then I've got the 7, which would go here. And so the act of doing this gives me an inserted list, a sorted list through every iteration. Every time I go through, one more element has been inserted into its right spot. So later on, if I was to get some more data values like a 6 and a 0 and a 3, I could say, hey, you know what? These first 8 are already in the right spot. Let's put the 6 in the right spot. It would go here. And so everything else gets shifted down. And then I need to put the 0 in the right spot. It would go here. So everything else would get shifted down. And then this 3, it would go right here. And everything else would get shifted down. So that's the idea behind the insertion sort. So let's talk about how we would code this. So I'm going to put my method header. Again, it's a private helper method. Private helper method. Private static void insertion with an int array called list. And what we need to do is we need to keep track of the key value. And we also need to keep track of the spot that we're going to move it into. So I'm going to set up my loop. So I'm going to say for int pass gets 1, pass is less than list.length, pass plus plus. And the reason I'm starting at 1 is because if I have a list with only one element in it, it's already in order. So I know that the list with just one element in it is already in order. I need to start with when I have 2 elements to make sure that list item is put in the right spot. And so what's going to happen is inside this loop, I'm going to keep track of my key. The key that I want to move is going to be list sub pass, and I want to put it in the right spot. So I'm going to set my key up to have that value, and I'm going to set up a loop. So for int, for spot gets pass minus 1, spot needs to be greater than or equal to 0, and list sub spot has to be greater than the key spot plus plus. Now, I'm going to talk about what I mean here. What's going to happen is because pass is starting 1 after the starting position. What I want to do is I want to look at all the spots before it. And I want to keep going backwards. That's actually should be a spot minus minus. And I want to go backwards as long as I still have spaces to go backwards to. In other words, I still have an index. I don't want to hit -1. And as long as the value that I'm looking at is bigger than what I want. In other words, I want to keep moving it to the left if it's smaller. And so as long as this is true, I want to set list sub spot plus 1 to get list sub spot. So the idea here is that when I had a situation like a 5 and a 9 and a 4 and a 8 and a 3, the thing is these first two numbers are already in order. If I want to put a 4 in here, I actually want to take the 4 completely out of the list. That's what we're doing when we say key gets list sub pass. I want to move the 9 over, so the 9 would actually move to this position. I want to move the 5 over, so the 5 would move to this position. And then this is the first time that I basically reach spot greater than or equal to 0. That's where I'm going to put 4 back in. So what I'm doing is I'm shifting each of these elements over. And now when I want to get to the 8, I'm going to take the 8 out of the list. The 9 is going to move over. And now this is the spot where the 5's not going to work, because 5 is smaller than 8. So I actually want the 8 to be here. And that's how this actually gets worse. Notice that this list sub spot plus 1 is being shifted over to list sub spot. And after I've gone through that list, I know that the spot that I'm currently pointing at is one behind where I want to go. So I'm going to say list sub spot plus 1 gets key. And so what I'm going to do is I'm going to run this code just to show you what happens. So I'm going to go up here, make sure I've got insertion sort as the sort that I'm going to be dealing with. We're going to run it, make sure I don't have any dumb errors in here. And of course, it sorts it. But remember, this isn't really showing what's going on. I'm going to go back to my Jelliet. I'm going to copy this code in there. I'm going to go to Jelliet. I'm going to paste my code in here. It's right after this. Let's go to edit. And then I want to take this insertion and have this being run in my main. So insertion. And we're going to compile it and run it. Now remember, it populates the list very quickly, and the 5 and the 9 are in the right spot. So it's checking out the pass. It's looking, key is the 9. The 9's what's going to be moved, but it's already bigger than the 5. So these first two are in the right order. Now I'm at pass 2, so I'm looking at where the 4 goes. I'm going to bump the 9 down. And then I'm going to bump this 5 down. And then this spot right here is where the 4 goes. So I'm going to put the 4 in that right spot. So now I'm looking where this 8 goes. The 9 is in the wrong spot, so I'm going to bump the 9 down. and then it's going to check this 5, but the 5 is in the correct spot. So I want to stick the 8 here. And then the 3 will bubble up to the top as well. And this is a very effective loop, because if I already have a list that's primarily sorted, I can just put the unsorted data at the end of the loop. And an insertion sort is actually going to be much quicker, because I don't actually do any swaps in those elements that are already sorted, unless I need to, unless I want to put the data in the right spot. So it's a very effective list for sorting. So I've got 3 techniques for sorting. I've got the action of sorting using the bubble sort, which is probably the easiest to code. I've got the selection sort, which probably works the fastest of our iterative sorts for when I have just a sheer amount of raw unsorted data. And then I have the insertion sort, which is very, very effective if I already have some data that's sorted, and I just want to kind of put extra data into that list. So now that I've got these 3 sorts, I want to talk about, what do we use them for? What's the purpose? And so I want you to envision a world where you live in a large city which has a population of tens of millions, and you want to find your friend's phone number. Are you going to look through and look at the first entry in the phone book, and then look at the second entry in the phone book, and look at the third entry of the phone book? Are you going to do that to find your friend's phone number in the phone book? Or are you instead going to flip to the middle of the phone book, and at the middle make a decision? Do I need to look in the front half, or do I need to look in the back half? That idea of breaking the list in half so that you have less to search through is a notion that we learn as children when we have to search for something in the index, or in a dictionary, or in a telephone book. And we can incorporate that here in our code. The idea is that we want to take the list and cut it in half. And then take one of those halves that has our data in it, and cut that list in half. And we want to keep going, cutting the list in half, cutting the list in half, until we find what we're looking for, or until we run into a situation where what we're looking for couldn't possibly be in the list. And the idea for this is called a binary search. So we're going to be talking about a binary search for the rest of this video. And so this is again is going to be a private helper method. So private static, but I'm going to return an int because I want to know where something is in the list. So I'm going to have some list, which I'll call list, and I'm going to have some integer, which I'm going to call my target. And so what's going to happen is I'm going to have a list. The very beginning of my list is 0. And the end of my list is going to be at the end of my list. So list.length minus 1. And I'm interested in the middle. Now the middle is going to be start plus end divided by 2. And I'm dealing with integers, so it's okay if I'm off by 1. We're actually going to deal with that in our calculations. But the idea is that I want to kind of go through this and go through this list until I run out of places to go. So I've got this notion of starting in the middle, keeping track of the ends and the starting points. And what I'm going to do is I'm going to say, hey, is this the place that I want to look at? So I'm going to continue this loop. And I'm going to do it using a while loop. We've talked a little bit about while loops in the past. While loops essentially keep running the same code as long as a certain condition is true. And I want to keep going as long as my starting point is greater than, or excuse me, is less than my end point. And as long as this is true, I want to keep looking for my data. So if what I'm looking for, target, is equal to list sub mid, then I truly am done looking for stuff, and I can actually break out of my loop, because what I'm looking for is exactly where I want it. If it's not, then I need to do the following. If it's not, I need to figure out which half I need to look at. So if target is greater than list submit, if that's true, then that means that what I'm looking for is in the top half. So don't bother looking in the bottom half. So in other words, I don't need to look at anything between list sub this middle and the beginning. So I want to change my starting point. I want to say start is going to be equal to mid plus 1. that's going to, in other words, basically say, hey, I don't care about the first half of the list. I'm changing my starting point. But if that's not true, then what I'm looking for is in the bottom half. So don't bother looking in the top half. So I'm going to say that my end, in other words, instead of looking at the back half of my list, I only want to look at the front half of the list. My end is going to be mid minus 1. And this idea of making start move forward and making end move backwards, either I'm going to find exactly what I'm looking for, in which case I break out of the loop, or this situation is going to happen. I'm no longer going to have the start less than the end. These 2 points are going to cross eventually if I'm not careful. So I'm going to, if this is true, do this, else do this, and no matter what, we need to look in a new spot. So I want to say that mid gets this start plus end divided by 2. And that's the end of this else, and that controls the while. So when I make it to this point, 2 things are going to happen. Either what I want is in the list, and if it's in the list, I want to return mid, because mid is pointing right at it. So if what I'm looking for is at mid, so if my target is there, then I want to return mid. If it's not, and I really don't need to write the else, because if I've already returned, then I'm never going to look at this line of code. But if I haven't returned, I need to return something. And remember that our error code when I'm dealing with ints is to return a -1. So here is our binary search. I'm starting by keeping track of the beginning and the end of my list, and I'm looking at the middle of my list. And as long as my starting point and my ending point are in the correct order, I want to keep going and searching. If what I'm looking for is in the middle, great, I'm done, and I'll return it. If it's not in the middle, then I need to check, am I in the back half of the list? In other words, am I too big? In which case, the middle needs to move to the right, so my starting point needs to move to the right. Otherwise, if that's not true, I need to look in the front half. My middle needs to move to the left, so my endpoint also needs to move to the left. In no matter what, if I reach this else statement, else means I didn't find it. So I need to keep looking for it. And so I'm going to reevaluate where my middle is based on where I've moved my starting point or moved my ending point. And I'm going to keep doing this as long as these are in the right order. But if they ever cross, if they ever get out of order, or if I ever find what I'm looking for, then I'm going to pop to the end of this loop. And if I found what I'm looking for, I need to let the user know, hey, I found what you're looking for. Otherwise, I want to return a -1. So what I'm going to do is I'm going to check this, compile it, just make sure it works. And yeah, I need to close. I think I've got an extra brace here. Let's see. Yeah, that brace doesn't go there. That's an extra brace. So let's compile this one last time. Still have another extra brace. Okay, this brace, can't tell exactly where it goes. That brace goes with that brace. So that's my extra brace. So that should compile correctly. So what I'm going to do is, after I've sorted this, I want to search. So binary search using nums as my list, and I want to know where the 3 is. And of course, after I run this, well, actually, I'm going to need to store that in a variable somewhere. So int location is equal to binary search, and I want to system.out.println 3 is in position plus whatever loc is. And so if I run this, it's going to sort my data, and it's coming 3 is in position 2, and of course notice that's my 0, that's my 1, that's my 2. If I'm searching for another number like 11, and I run this, then 11 is in position -1. So there is no 11 in my list. So the last thing I want to do is I want to take this notion of a binary search. I want to copy this code, and I want to paste it into my Jelliet, just to kind of show you what's going on there. So I'm going to paste this in at the end. And then I also want to paste a call to it. So just like I did before, go to my main, and I want to copy these two lines of code. And I'm going to put it at the end of this. Now, again, I want to show that I'm looking for a 3, and that something works out well. And the sorting is going to take the longest amount of time, so I probably will cut the sorting out. And I'll join you when the sort is done. So we're just about to put the 1 in the right spot. The 1's going to go into the spot right here, and then I'm going to pause this. And then I'm going to hit this step notion. The idea is that I can go through this step by step. So 9 less than 9 is false. This is going to exit the loop. And this takes me back out to my main method. So now we're going to do the binary search. I'm going to go step by step through this to show you what's happening. So I'm just going to adjust this so we can see the code as we step through it. So we're passing the array in 3s to this binary search. Start, see it's set to 0. The end gets set to the list -1, which is 8. And the mid is going to be 0 plus 8, which is 8. And 8 divided by 2 is 4. So now, as long as this is true, as long as 0 is less than 8, which is true, so we enter our loop, we're going to check and see if 3, the value that we're looking for, is equal to whatever's in box 4. Notice there was a 5 in box 4. And it's not. So we need to go into the else branch. And inside this else branch is what I'm looking for, a 3 greater than 5. And that's false. So again, we're going to go to this else branch and set end. End is going to be the middle -1, which is position 3. So now at this point, I know that I don't have to look at 5, and I don't have to look at anything past 5. All I want to look at is from 0 to 3. I know the number I'm looking for is somewhere in here. So my new middle, if I take 0 plus 3 and divide it by 2, I get 1. That's my new middle. And now I'm ready to go through the loop again. Now, 0 is still less than 3, so we're good. We're going to keep searching. So, is 3 equal to 2? Nope. So we hit the else branch. We need to reevaluate. Are we in the top half or the bottom half? And 3 is bigger than 2, so I want to be in the if branch. So I'm going to change my starting location. My starting location is going to be 1 up, and that means now I know I'm not from 5 down, and I know I'm not from 2 back. I'm either in position 2 or in position 3. Now I know that we're looking at 3, but I can see the entire list, and my computer can't. So it's going to have to go through this one more time. It's going to evaluate a new middle based on its starting and ending position. And then we're going to go through. Now 2 is still less than 3. So we go into the while loop. What are we looking for? We're looking for a 3, and 3 is equal to what's in box 2. So that's true. We go to the then branch. We break. This dumps us out of the while loop. And now we go to this if statement. What we're looking at in box 2 is a 3. And that is equal to our target. So we return the value. We return mid. We go back to our original function. And now this location that we were looking for is going to be 2. So now we go to the system out print line. We concatenate 3 is in position 2, and then we print it to the screen down here. So that's kind of how a binary search works. Notice that a binary search, because it cuts the list in half every time, it's very cost effective when it comes to time and memory. If I had 1,000 items in a list, to find the average item using the linear search we talked about a couple of days ago would take about 500 searches. Because there's sometimes what I'm looking for to be right at the beginning of the list. It only take 3 or 4 searches. And there's sometimes where it'd be at the end of the list. It would be at 990 or 995 searches. But with a binary search, we're always cutting the list in half. And so we're cutting the number of boxes we need to search in half. Half of 1,000 is 500. Half of 500 is 250. Half of 250 is 125. Then 62, because remember we're doing integer division. Half of 62 is 31. Half of 31 is 15. Half of 15 is 7. Half of 7 is 3. Half of 3 is 1. And by that point, after 9 subdivisions, 9 searches, we either know what we're looking for is in the loop, because we're pointing at it, or it's not in the loop, and it must not be in the list anywhere else. And that is the power of having sorted data. It may take a while to do it, and there's lots of different sorts to do. We're going to continue talking about sorts in the upcoming months, but these 3 sorts sorts are going to be good enough to get us through some basic tasks. So, once again, this is Mr. Potter. Thank you for watching. Have a great day.